Introduction to Antimatter. Antimatter is one of the most intriguing and enigmatic concepts in modern physics. It is the counterpart to regular matter, consisting of particles that have the same mass as particles of ordinary matter but opposite electrical charges. Despite being predicted by theory and observed in experiments, antimatter remains shrouded in mystery and fascination. The basics of antimatter. In simple terms, antimatter is composed of antiparticles, which are the antimatter equivalents of particles found in regular matter. For example, the antiparticle of the electron, which has a negative charge, is the positron, which has a positive charge. When particles and antiparticles meet, they annihilate each other, releasing energy in the process. Historical context. The concept of antimatter was first proposed by physicist Paul Dirac in 1928. Dirac's equations predicted the existence of particles with opposite charges to those known at the time. The positron was discovered in 1932 by Carl Anderson, confirming Dirac's theory and marking the first direct evidence of antimatter. Creation and detection. Antimatter is produced in various ways, including high-energy particle collisions in particle accelerators and natural processes such as cosmic ray interactions. Scientists have also created and studied small amounts of antimatter in laboratories. Techniques for detecting antimatter involve observing the annihilation events that occur when antimatter encounters regular matter. Antimatter and the universe. One of the biggest mysteries surrounding antimatter is the apparent scarcity of antimatter in the observable universe. Theoretical models suggest that the Big Bang should have produced equal amounts of matter and antimatter. However, our universe is predominantly composed of matter, leading to questions about why there is an imbalance. Baryon asymmetry. The discrepancy between matter and antimatter is referred to as baryon asymmetry. Various theories attempt to explain this phenomenon, including the idea that processes in the early universe might have favored the creation of matter over antimatter. Experimental research in particle physics seeks to understand these processes and the underlying reasons for the imbalance. Applications and research. Antimatter has practical applications, including in medical imaging techniques like positron emission tomography, PET, scans. Research into antimatter also holds potential for future technologies, such as advanced propulsion systems for space travel. However, producing and storing antimatter remains extremely challenging and costly. Challenges in antimatter research. Studying antimatter presents several challenges. Creating and containing antimatter requires sophisticated technology and high-energy environments. Antimatter must be stored in vacuum chambers using magnetic fields to prevent it from coming into contact with matter, which would lead to annihilation. Theoretical implications. Antimatter also has significant implications for fundamental physics and cosmology. It challenges our understanding of symmetry and the fundamental laws of nature. Research into antimatter continues to explore its role in the universe, including its potential connections to theories such as supersymmetry and dark matter. Future directions. The future of antimatter research holds promise for uncovering deeper insights into the nature of the universe. Advances in particle physics, experimental techniques, and theoretical models may eventually provide answers to long-standing questions about antimatter and its role in cosmic history. Conclusion. Antimatter remains a profound and captivating area of study in modern physics. While scientists have made significant strides in understanding its properties and behavior, many mysteries persist. The quest to unravel these mysteries not only advances our knowledge of the universe but also pushes the boundaries of science and technology.